Hello everybody and welcome to this project on image super resolution using the SRCNN network. This is going to be a really exciting project where we are going to quite literally do what CSI Miami would say is enhance or image enhance. We are going to take low resolution images and produce high resolution outputs using this super resolution convolutional neural network, which was published in this paper at the very end of 2014, started 2015. So as usual, we are going to be using Jupyter notebooks, and so let's go ahead and get started with that. First things first, just open up the terminal. In Windows, command prompt. I'm going to CD over to my tutorial folder and then start the Jupyter Lab right here. So in the past couple projects, we switched over to Jupyter Lab instead of Jupyter Notebook. Jupyter Lab was just released, and it gives you some convenient benefits over just individual Jupyter Notebooks. However, you could use either one. Obviously, I'm going to be going with Jupyter Lab, and you will see why it comes in handy a little bit later. It's going to have, over here it shows the current folder, the directory that you are in, and we're actually going to populate this with a couple different folders and files in this project. So it's helpful to be able to see this over here. Right now my tutorial folder is empty. That's why you don't see any files in there now. Alright, so I'm just going to go Python default, which is and now you actually get the file over here. Python default is Python 2.7 for me, but we will check that and make sure in a sec. So let's go ahead and rename this. Let's just call it Super Resolution, because that's what we're going to be doing today. Alright, first things first, I'm actually just going to copy in some background information here for you into this first cell. I'm going to make it a markdown cell. Shift Enter goes ahead and formats this. So here's what we're going to be doing today. We are using the super resolution convolutional neural network. It's published in the paper that I just showed you right here at the end of 2014, started 2015. We are going to be implementing this network in Keras. It was originally built using MATLAB. However, there's a lot of licensing issues around MATLAB, so we are going to be building it in the free and open sourced Python and Keras. Also, one thing that we're going to be doing today is we're going to be using the OpenCV, which is the open source computer vision library, to do our image processing for us. This is a library that we haven't used up until now, so what you're going to have to do is probably install that unless you already did. A more recent advancement has allowed us to just get the Python binaries for this. This is actually developed in C++, so it's a C library. However, there's pre-built Python binaries for us, so as usual we can do a pip install, and then it's actually going to be OpenCV Python. And so this is going to get you the OpenCV binaries for Python. So go ahead and do that if you haven't installed OpenCV or used OpenCV in the past. And we're also going to be using the typical Keras, NumPy, Matplotlib, and the scikit image. You should have all of these by now, but just in case, let's go ahead and start with checking our package versions, and we're going to do that by importing a few of these these libraries and packages really quick, and then just printing out their version numbers so that we can make sure that we are all on the same page. This is an important step for reproducibility, and as well it's going to help us avoid getting errors down the road that could be based on the versions that we're using or something like that. So this is always a good idea to start with, and it's something that we've been doing in our previous projects as well. So let's just get these typed out here really quick. They should all import correctly because I have all of these installed. If you get an import error on one of these, it's because you don't have the correct library installed. So it's really important that we're able to do this step. to ensure that everything is installed correctly. So just a couple of these here. Let's get the matplotlib. And as always, the dot format is going to be substituting in a variable into the string. So that's why I'm using that. And last one here, this is actually the scikit image package. We've been using scikit-learn in some other projects to deploy machine learning networks. The scikit image is going to give us actually one of our image quality metrics that we're going to be using to evaluate our network today. Alright, so now that I have this, should be able to go ahead and click Shift Enter, and that'll run. So this is some information from Keras that's actually coming right now. This is from one of it's the H5Py package. We're actually not going to be using that, so we can go ahead and disregard this warning here. So here we go. Here's all of our print functions. We have the Python 2.7, which I just mentioned, and then Keras, OpenCV, NumPy, Matplotlib, and skimage, the scikit image package. So here's the versions I'm using. It isn't entirely important that you're using exactly these versions. It is probably important that you're using Python 2.7. Alright, so let's move on. Looks like we have everything installed and we are ready to go. But as is usually the case, we don't just need Keras in general, we need some specific model types and layer types from Keras. So in this cell, we are going to import some more specific packages from these different libraries. So from Keras.models, we are going to import sequential. We are going to be defining a sequential model today, that's our srcnn. From Keras.layers, let's import conv2d, this convolutional layer. We're going to also be having an input layer, and that should be it. From Keras.optimizers, we are going to import the stochastic gradient descent as well as atom. We'll have the atom optimizer today. And then from skimage.measure, we're going to be importing the compare SSIM, which is the structural similarity, as SSIM. This is one of the image quality metrics that we'll be using in this project to evaluate our performance of our network. So we are also going to be using the peak signal to noise ratio, the mean squared error, and then finally the structural similarity index. So these three image quality metrics give us a pretty good wide range of different metrics. So we'll see if some are better than the others, if perhaps we improve our structural similarity but not the mean squared error, vice versa. It's a good idea to have multiple image quality metrics because one by itself doesn't always tell the whole story. Alright, so let's keep going. From matplotlib, let's import pyplot, and we'll import it as plt. And then we need to import cv2. We really don't need to type that again, but that's okay. Just for readability, we'll have it there. We'll also need the math functions. This is pre-built into Python, so you don't have to install anything there. And then import OS as well. Alright, and one last thing we need to do here is a Python magic function. And this is going to be the matplotlib magic function inline. So this is going to tell Jupyter Notebooks or IPython to plot these graphs or images that we're displaying in the notebook itself instead of doing like a different pop-up window or something like that. So this is kind of a formatting here. It's a magic function as denoted by this percentage here. And so that will format everything for us and make it all nice and pretty. Alright, so Shift Enter, make sure everything runs there. And we get all of these imported correctly. And we should be good to go, and yes, it works. We see the 2 there, so it means it's done. And we are ready to move on. Alright, so to start, we are going to define our 3 quality metrics. So we'll start with the peak signal to noise ratio. We actually have to create a function for this one. So we're going to define a function for peak signal to noise ratio. And this is PSNR. Okay, so creating a Python function here. We'll have def PSNR. We're going to have a target image and a reference image. So those are going to be our two imports or inputs into this specific function. The peak signal to noise ratio, mean squared error, and structural similarity all compare an image to a ground truth or reference image. So what we're actually going to have here is we're going to produce low resolution images from a high resolution image and compare the two and calculate these scores that way. So let's go ahead and define this. So we're going to assume an RGB image. And it actually could be a BGR as well. So we'll have target data equals target.asType float. So we're going to convert all of the integers in this target image to floats. And we're actually going to do the same thing for our reference image. So asType float, this will give us decimal values instead of whole integers. We are then going to calculate the difference between the two images. So we can do a simple subtraction there, but we are going to have to flatten this so that we can do some computations with it in a sec here. And here we're going to have the root mean squared. So this is where our math is coming in. We're going to use the math square root of the numpy np dot mean of the difference squared. And you do a squared with this double asterisk here in Python. And we're actually going to put a decimal point here so that we know that this is a float, so that we have float values and decimal values coming out of this. All right, and we're good to go there. And then we want to return. We got to do a couple more manipulations here. Math.log10 and then the 255 dot to denote a float divided by this RMSE, which we just defined. So this is the formula for the peak signal to noise ratio. You can look this up online if you want. This is just a simple way to define it, and then we'll be able to call this function later. All right, so let's move on. We want a mean squared error. Squared, there we go, error. And we're going to have a similar function for the mean squared error. So let's define the MSE, again, between the target image and the reference image. So those are our two inputs. So MSE here, mean squared error, is the sum of the squared difference between the two images. So very similar to peak signal to noise ratio, however, some subtle differences. We're going to have the np.sum target.asType. So again, we're converting them to floats. We're just going to do this right in the function here. Minus reference.asType float. And then we have to square this, which we do with the double asterisk once again. All right, so there's that. And then we're going to be dividing by, so divide by equals just means divide this previous value by the following. And that's going to be a float target.shape 0 times target.shape 1. So this is the total number of pixels or values that we have. And then let's go ahead and return this. So return error. There's our mean squared error. That function is defined. If you look up above, we actually imported the structural similarity as a function. So this is already, the structural similarity is already defined for us. So we don't have to do another function for that. But what we do want is to define a function that combines all three image quality metrics. That way, when we're later evaluating our performance, we don't have to call all of these individually. We can just call an individual function that is going to give us all 3 metrics. So let's do a compare images. And again, we'll have our target, we'll have our reference image. And let's just make a list of scores here. So brackets, empty brackets, this is an empty list in Python. And we're going to append to this the peak signal to noise ratio of our target reference. So we're calling that function that we just defined above. We're going to append to this the mean squared error target reference. And finally, we'll append to it the structural similarity of our target and reference. And we actually have to set another parameter here, multi-channel equals true, so that this will handle 3-dimensional images or 3-channel images, RGB or BGR, whatever the case might be. Alright, so there's all of those. And we actually have to have a return scores here as well. And we run this, and we didn't actually call any of these functions. We just defined these functions, so it goes really quick. And we should be good to go here. We have our 3 functions that we need. We have the peak signal to noise ratio, the mean squared error, and the structural similarity. So these are the image quality metrics that we're going to be using, and we will be testing those out in a second here. But first, we need to prepare the images. So actually, one thing that we're going to have to do is we're going to have to download some images to use in this project. And we are actually going to be using the same images that they did in the original SRCNN paper. So those can be found at this link here. I already have this open. This is image super resolution using deep convolutional networks. This is kind of the source code for the original paper. And so down here they have some codes. They originally implemented this in MATLAB. They also did Caffe. We're using Keras, and that's why we're typing this out again. But if you download this zip file, it actually is going to have the images that we want in there. So here I have my downloads. If I go into this file, you can see that they have the set 5 and set 14. These are 2 different sets of images that we are going to be using in this project. So what I'm going to do is I'm going to do extract all, and I'm not going to go into my downloads folder. I'm going to go over to tutorial, and then I'm going to make one more SRCNN, so I'll put it into its own folder here. And let's go ahead and extract those. Okay, there's that. And then here's this folder. So we have our tutorial folder. We have the Jupyter notebook that I am defining now, or we are creating right now. And then now we have this SRCNN folder as well. So if we go into here, we see the set 5 and set 14. I'm going to take all of these. They have 5 images and then 14 images respectively. Control A, and I'm going to copy these, go back to tutorial, and I'm actually going to make a new folder here. I'm going to make a source folder to hold all of our original reference images. Okay, and we can go ahead and paste those images directly into this folder. So we'll paste these here. We are thinking, there we go. So we got those 5 images here, but we also have some other ones as well. If we go back to this guy, over here in the set 14, we have some more images. We have 14 images here. One thing to note though is that we do have 2 grayscale images in this one. We're going to go ahead and delete these and only work with 3-channel images right now. So just get rid of those. We don't need them. And then these 12 other images, I'm going to Control C, copy these, come back over to the source folder, and then paste these in here as well. So we'll get these in there. Alright, and so these are going to be our source images. These kind of serve as a ground truth, high quality type image. And now we're actually going to use these to produce the low resolution images that we're actually going to be using for the super resolution convolutional neural network. So let's go ahead and go back to the Jupyter notebook. We have our image metrics functions. We have our images now. So let's move on to actually preparing the degraded images. So prepare degraded images by introducing quality distortions via resizing. So we're going to use OpenCV to resize these images, and we are going to define a function called prepare images that will do that for us. So let's go ahead and do that. So def prepare images, and so we're going to have a path to the image file that we want here, as well as a factor. So do we want to resize these up by 2 or down by 3, whatever the factor might be. So we'll have some variability in that. Alright, and for this as well, we are going to loop through the files in the directory. So whatever our path is, we'll consider that the directory. And then for the file in os.list directory, that path. So this is essentially just going to give us the file name for every single file contained in whatever path. We're going to be feeding this our source folder, of course. Alright, so let's go ahead and open the file. We're going to use CV2 for that, the OpenCV. So we can use imread, and we'll simply do a path plus, we'll give it a slash here just in case it's not included in the path, and then the file name. So whatever the path is, and then the file name in that path. So we'll open up our image, and then we need to find some of the dimensions. So we'll find old and new image dimensions. And to do that, we'll simply do height, width, and then C here is channels, and we'll say equals image.shape. And now here's where our factor is going to come in. We're going to generate a new height, and so we want to actually downsize these images because that will give us better low resolution images. So we're going to do, the new height is going to be height divided by factor. So if our factor was 2, our new height would be half of whatever the half was. And then new width, same thing, equals width divided by factor. So there's that. And now we're actually going to resize the image. And this first one was going to be down, so we're going to resize it back up afterwards as well, so that we have the same size of images. We don't have really small images, but they're just going to be lower resolution. So we'll use CV2 for this again. CV2, resize, and that same image that we opened above, we'll give it our new width. It's important to note that the width comes first here, not the height, and then new height. And now we actually have to define an interpolation kernel. So what we're going to be using is something called CV2 interlinear. This is bilinear interpolation. If you're familiar with computer vision or images in general, you might have heard of bicubic interpolation, bilinear interpolation, and then there's also nearest neighbors interpolation. So these are different methods of resizing images. You know, how do you go from an image that only has a couple hundred pixels into it to one that has 1,000 pixels in it? So nearest neighbors is the simplest of those three. Interlinear, or the bilinear or bicubic, they end up actually doing some transformations on the pixel data to kind of smooth out the information a little bit. If you see like those really pixelated blocks when you zoom way into an image, that's going to be the nearest neighbors interpolation. Anyways, that's a little bit about image resizing. We are using the bilinear. So there's the resize down. Let's resize the image back up. So to do that, we're going to have the same thing, cv2.resize image. We'll go back to the original width, the original height, and once again, interpolation bilinear. Alright, so there's that. And I believe actually the default interpolation for OpenCV is bilinear interpolation, so we really didn't have to define this, but just for the sake of readability, since this can be kind of important, we're going to include that there. Alright, and then we can save the image. We're also going to do a print function for this purpose, so we know which one we're using or which one's saving. We also know that the function is running. So format file, so saving file, we're going to do cv2.imwrite images slash, we'll give the brackets here and then substitute in, we'll give it the same file name and image. So we're actually going to have to create a new directory over here. We'll call these images. So we have our source directory now, our images directory, and we're going to save all of the low resolution images into the images directory. Alright, so here's our function. We're good to go. We can go ahead and click Shift Enter on this. This is just defining the function, so we haven't actually ran anything yet. But we can do that here by going to, oh, I selected the wrong cell. There we go. We'll just call this function now. We'll do prepare images. We'll pass it our source directory as the path. And then for a resizing factor, we'll just do 2. So going down to half the width and half the height, and then resizing it back up. So let's go ahead and run this and see what we get. So wow, really quick actually. Oh, one of the good things about OpenCV, and remember it's designed for real-time computer vision applications, so OpenCV is incredibly fast. And that is kind of true of most C++ libraries or C libraries. They're generally going to be a little bit faster than Python code. So there we go. Let's actually go into this and see some of these. So if we go back to our tutorial folder, now in the images, we have all the ones we just generated. So these are actually lower resolution. So maybe we can pull one of these up to kind of see that. So if we have this one, let's pull up the reference image. So source. So we had the butterfly. So this is going to be the high resolution one here. We'll pull open this. So there's that. And then here's the other guy. So you can see those two. We have a high resolution, and because of the resizing that we did, we've now produced this lower resolution image that is the same dimensions as it was before. It just has, it's a lower quality. It's got these image distortions because when we downsized it, we had to store all this pixel information in a smaller area, so we lost some of the pixel information between these two images. Anyways, so we can see visually that it looks degraded. Let's actually go ahead and run all these images through our image quality metric functions that we defined above. So then we can actually prove that yes, these are lower quality images, the degradations worked as they should have, and that type of thing. Also, we're going to be ensuring that our metrics that we defined above here, that these don't have any errors. And I actually did have some spelling errors here, but I've fixed those now. So if you saw me type something that was not scores or append earlier, go ahead and fix that and double check that you have those correct up there. Or if you get an error, it's probably right there. Alright, so let's go ahead, and what we're going to do is we're going to be testing the generated images using the image quality metrics. Alright. So once again, we're going to be looping through all the files in the directory. So we'll do a for loop. For file in os.list or list directory is what that's short for. We'll have images. So we'll pass it our images folder. And so this is just the file name. We got to go ahead and open up the image. So we're going to open the target and reference images. So first one is going to be the target. These are going to be our low resolution images. So imread images slash, and then brackets is just going to be a .format file to substitute the file name into that string. So reference equals cv2.imread. These are going to come from the source folder. We want the high resolution images for this. Brackets.format, and since they have the same file name, we can pass them just that file once again. Alright, finally, we'll calculate the scores actually. So we'll have scores equals compare images, which is that function we defined above that calculates all three, the peak signal to noise ratio, mean squared error, and structural similarity. So we'll call that. We will pass it both the target image and the reference image. So target, low resolution, reference is the high quality or ground truth image. All right, and let's go ahead and print these out. So print all 3 scores. And we're actually going to be doing some formatting here. We want this to look nice. So we're going to print out the file name. And so we can do a brackets, and we're just going to do a dot format, and we'll substitute the file in. But we also want to do a new line character here. So a \n is going to be a new line character. So it's going to bump us down to the next line instead of printing this all out in one continuous line. So we have peak signal to noise ratio first, and then we'll do once again a new line mean squared error, brackets, because we're going to be substituting these in, and then finally structural similarity. We'll get that guy on there as well. And we'll add one last new line character onto the end here, separate these out between images. So now we substitute in our variables. So first one was file, then the peak signal to noise ratio is going to be scores 0, scores 1 is mean squared error, and then scores 2, the third score, second index, or index 2, is going to be our structural similarity. And that's just because of the way that we were appending these scores up here. The scores is a list of length 3, peak signal to noise ratio, mean squared error, and then structural similarity. So those should be all those. Alright, and let's go ahead and see if this worked. So we'll run Shift-Enter, and indeed it does. So for our first image, we have the baboon, peak signal to noise ratio 22, mean squared error 1000, and then structural similarity all the way down here at 62. So structural similarity, we'll start there. Structural similarity of 1.0 would be exactly identical images. So this is going to range from 0 to 1, 1 being a perfectly identical, 0 to be completely different. So this is definitely degraded. It's 0.62. It's not that similar. Mean squared error, the higher you are here, the lower resolution image you have. So a mean squared error of 0 would once again be a perfectly identical image. The higher your mean squared error, obviously the more error that you have. Peak signal to noise ratio, we actually want this to be as high as possible, which makes sense because we want our noise to be really low. So peak signal to noise ratio, if we have low noise, we'll have a higher score. So the higher the PSNR is, the better. And this can vary dramatically since we had some logs in the calculation of this. So there's our 3 scores. For each image, we are degraded. Just looking at the structural similarity and the mean squared error, you can tell right away that we introduced some degradations into those. Some of them more than others, so that's good. We have some variety in the quality of images that we have here as well, but all of them appear to have a lower resolution than the original source image, which makes sense since we resized them all. And we should be good to go. Furthermore, it looks like all of our image quality metrics are functioning properly. They are all calculating. We don't have any errors in our code, so we are good to go on that front too. Alright, so we've hit that point. We have prepared all of the images that we need. We've produced the low resolution images. We have the image quality metrics defined. They're easily called using this compare images function. So we are good to go to head on to building the actual super resolution convolutional neural network. So we're going to define that model, but we're actually going to do that in the next video to keep these at a reasonable length. So thanks for listening to this one, and keep following along with me, and we'll get to actually building and deploying the SRCNN model. Thank you very much.